Hey everybody, today I am doing another math problems, and we are going to do another limit problem. Okay, so but before we do the problem, I'm going to explain a little bit how this limit process is going to work, because now we are going to be dealing with exercise 2.4. It's called limit involving infinity. Okay, so it's going to be, like I said last time, that we need to be analytical when we solve these problems, and that's what we're doing basically. Okay, so the section that we're studying is on 2.4 in this book. Okay, calculus, the classic edition. Okay, and this you can find this theorem on page 75, starting on 75 at the bottom, and page 76 in this book. Okay, so first I'm going to go through real quick on how this limit is going to this limit is going to be solved, right? And the definition is very long. I didn't have enough room to copy everything down because it's way too long. I just wrote the most important pieces that we need to take in consideration. Of course, you can take the whole thing in consideration, but in my case, it's too much to write on this board. There is no way that I can fit everything in this little board that I have. Okay, so we are going to find the limit when the function are going to infinity. Okay, so if the function are going to infinity, we are going to try to find the limit and identify if the limit exists or not, right? So in this case, we have the limit of f of x equals infinity, right? At x goes approaches a, right? Means, I'm missing an s right here. Means for every m greater than 0, there is a delta, okay, greater than 0. This delta is a Greek letter delta, right? Such that if the absolute value of x minus a is greater than 0, and the same absolute value right here is less than the delta, which is the Greek letter delta, then f of x is greater than m, right? Now, that means that we have an interval, okay? We have an interval between, okay, we have an interval approaching from both sides, right? So we have x minus the Greek letter delta, and we have x plus the Greek letter delta, right? Now, and x cannot equal 8, okay? X cannot equal 8, okay? So that's a very important, okay? So x cannot equal 8. Now, okay, point on the graph lies above the horizontal line, okay? Very important. Point on the graph lies above the horizontal line, okay? The limit of f of x, and then look at this. If this line right here lies, if f of x is greater than m, right? It lies above the horizontal line, okay? Now, if we want to go get this line down here on the negative, I didn't write it down because, like I said, it's too long. But what it is if I if I want to get this line on the negative side of the horizontal line down here, okay, I have to say the limit of f of x equal negative infinity if we replace m greater than 0 by n less than 0, right? N, f of x is greater than 0 by f of x is less than 0, okay? Now, look at this. This is a graph that represents this theory, okay? Look, I have two functions, okay? It seems like I have a function that is increasing in that direction and another function that is kind of decreasing from this direction, okay? But at the same time, they both going up without touching each other, okay? Without touching each other. At the end, it's going to be like a very close to parallel lines going to infinity, but not necessarily touching each other, right? Why? The question is why? Well, because this interval right here, these two intervals, a minus delta, okay, and a plus the Greek letter delta, okay, again, a minus the Greek letter delta, and then this one right here, a plus the Greek letter delta, they are approaching to each other, okay? So this one is approaching this way, going from positive, okay, from positive to negative, getting close to a, to this vertical line. You can see that as a vertical asymptote, okay, but it's going straight here, but not necessarily touching it, okay? So delta a plus delta x, right? So delta is not this interval right here is not touching a, and this interval right here is not touching a, okay? So they are close but not necessarily equal, okay? They are getting very close to a but not necessarily equal, because if this approaches a and if this equals 8, I'm sorry, then this statement won't be true, okay? So because the point of limit is that a certain interval is approaching a certain number but not necessarily equal that number, okay? So I'm going to erase this, and I am going to do a problem, okay? Because I need the room. I can't keep this and do the problem. I don't have enough room, okay? So I am going to use number 15. Okay, we're doing number 15 on this book. So number 15 is limit limit 2x squared minus 3 over 4x cubed plus 5x. Okay? Now, in this case, x approaches negative infinity. Okay? X approaches negative infinity. Okay? Now, let's work it out. Okay? Let's work it out, this problem. First, let's analyze the problem. How the problem look like. Okay? What is the stuff that I have in this problem right here? What is that I have to take in consideration? Okay? Well, first I have to look at the exponent, right? The exponents of this expression right here, the exponents of this expression, the bottom is higher than the top. Okay? So the bottom exponent, the bottom is higher than the top. Okay, so in other words, the degree of the bottom is higher than the degree on the top. I'm sorry. But now, what can I do? What can I do to kind of analyze this problem? Well, if you see right here that the top degree is less than the degree in the bottom, you can actually assume if you replace any number by infinity over here, it's going to go to 0, right? And also this 5x, if you plug in infinity, is going to go to 0, right? So why? Because the top number is less, the top degree is less than the bottom, right? Degree. Okay, so but to make it more visual, what I'm going to do, I'm going to go ahead and divide everything by the highest power. Everything by the highest degrees, right? So in this case, what do I get? I get 2x squared, right? And I get 3, I'm sorry, just 3, okay? So what is the highest degree? The highest degree is x cubed, right? So I'm going to divide that by x cubed and divide that 3 by x cubed, right? Then I'm going to divide 4x cubed divided by x cubed, right? And then plus 5x divided by x cubed. Alright? So now, look at this. Okay? At limit, right? I'm taking the limit of this, but first I want to see if anything cancels out. Okay? So this one right here doesn't cancel anything, right? 3 divided by negative 3 divided by x cubed, right? Doesn't cancel anything. But this one right here cancel that x squared on the top right there, cancel with x squared at the bottom, and leave me with x, right? Then this one right here, x cubed, cancel with that x cubed, right? And then this 5x right here divided by x cubed, 1x on the top, cancel with 1x on the bottom, which is leave me with x squared, right? Now, what I'm going to have is 2x, I'm sorry, it's not 2x, it's just 2, right? 2 minus 3 over x cubed, right? Then I get, okay, this is 2 over x, right? Then I get 4, okay? And then I get 5 over x squared, right? Limit as x goes to negative infinity, right? Now, let's try try what is going on right here. Let's see what is going on. Well, if I plug in a number right here that goes to negative infinity, what is going to happen? Okay? So if I plug in a number that goes to negative infinity, right here, this is going to be kind of bigger number. But if I apply a number that is negative right here, and this is the cube, this is going to make a negative number at the bottom times this positive is going to make positive, right? The negative, if I plug in a negative number in this x cube, it's going to give me a negative number, right? Because I am cubing it. Okay? If I multiply by that negative sign, it's going to make a positive. Okay? And then if I plug in negative infinity in that x right there, it's going to make negative number, right? Well, this number is going to be greater. If this number is going to be greater, and then it's going to eventually, this is going to reduce to 0, because if you find a common denominator between these two, this number is going to be greater, and then you multiply this number by this number, okay? Everything eventually will go to 0 because this denominator right here will explode. It will go to a big number, to infinity, which is going to leave this top going to 0, right? Now let's do this one, okay? So this one right here, if I plug in 5 divided by that number again by negative infinity, is going to also doesn't really matter because I already have a top I already have a 0 on the top, right? So if I replace negative infinity by that, it's going to get infinity smaller. But if this number goes infinity smaller, and this value right here is going to be this form right here is going to be very, very small number, which is going to be just pretty much just 4, right? Okay, so, but 0 divided by 4 is 0, okay? So that is the answer for that, okay? So, again, this is one of the problems that we need to be little analytical so we can actually understand what's going on, because it makes sense. Because see this limit, when this is coming closer and closer to a, at some point the limit over here is going to equal 0, right? In this case, because this is only one example, right? For the graphical representation. But in this case, because we had an x cube at the bottom, okay, it's going to make this number right here, okay? So if you divide that this 2 over x right here, okay, this 2 over x is going to be like a slope, a graph starting at 0 and kind of taken up, right? Taken up very, very quick. Why? Because remember that any graph that look like 1 over x, right? 1 over x will have a graph like one piece going like this on the Cartesian plane and another piece going like this on the Cartesian plane, but not meeting at this line right here, because at x equals 0 this function will be undefined, okay? So that's why it's one of the things that we will take in consideration in order to solve this problem. And I hope this helped anybody who is taking limits in Calculus 1. Again, the most important thing is to analyze the problem and the techniques that we need to use by canceling the numerators and the denominators by dividing the expression by the highest degree, right? By the highest degree, that's how we simplify this. Again, I hope this helped anybody who's taking Calculus 1.